if you recall in the last class, we were of course in Unit 3, and then let me take you to a slide where what we are doing. So we're talking about how to implement the linked list, right? So we said that this is the basic node implementation where we have a struct node. There are two things that go into the structure. One is the data, because linked list has two things. One is the data, second one is the link to the next node. So we looked at this structure, okay, and then I gave a full program which shows various functions of how to create the linked list, how to insert elements, how to delete elements, and how do you insert at the beginning, how do you insert at the end. These are all the functions that you see here, right? Element, whole permutations and combinations. Okay. Then I gave you the structure where in the main, the user is prompted saying, hey, what do you want to do, right? Do you want to insert at beginning, delete at beginning, insert at end? Choose one of the numbers. If it is 1, in this case, insert at begin. 2, delete at begin, and so on. Okay? Then once the user enters the input, we did a switch of the input, the standard statement, right? Anything more than a couple of if-then-else's, we use a switch. So in case 1, we know that it means it is inserted at the beginning, as we see in statement line 4 here. Okay? So once you say insert at the beginning, somebody is trying to talk, you want to put it in chat? Okay. I'm seeing somebody, I'm muting SVCW, if I can. Okay, 1 second. Can you mute yourself, please? Hold on. I have to stop sharing and then mute all of you again. Okay. So I have muted all the participants. I'm still getting static. So okay. Looks like a SVC. Can you hear me? Okay. So you're saying there's no audio. Can you hear me now? I have no clue because the audio looks fine on my side. Okay, it is what it is, right? You can even hear my dogs barking. Somebody came outside. So hold on a second. Okay, so now if you see, since it's the very first node, we said, hey, make node pointing to the very first node. You get the value 25 saved there, and then at the very first node, the next has to point to null. Now pretend, okay? So pretend you want to insert the next node, okay? I'm going back to the head is already there. Now head is pointing to what, by the way? If you go back here, if you see head is pointing to make node. So head would have value. If I have to write head here again, give me a second. By the way, I don't have the chat open in front of my eyes. If somebody has problem with the audio, put it again in the chat. I'll notice it. So, okay. So DMS S3 does not have they can't hear me, but Chakravarti Garu can hear me well. What about JNTUV? JNTUV, can you hear me? Put it in the chat. Can JNTUV hear me? Okay. EMS, it could be a problem at your end because everyone else is able to hear me. Check it out. Hopefully you can hear me soon. Or send a note to Chakravarti Garu. JNTUV, you took control. Why do you need the control? Do you need the control or can I take it away from you? Okay, I'm taking control back. I don't know why you wanted the control. If you need control, okay, continue. Perfect. Okay, so we got the 25 null. Now what I want you to tell me is, and now head is equal to, head is pointing to 9999, correct? At the end of the, okay, I'm continuing JNTUV, so please don't take control. Let me disable you. Hold on. No, nobody can share, okay? Okay, if anybody wants to sell something, put it in the chat. I'm monitoring the chat. Okay, so head would be 9999. Okay. Now, if you want to insert the next node, okay, I will leave it to you as an exercise. See how you build this node. Okay, that's one thing. That's the only way you can assimilate what is being told, right? With respect to preparing for your either midterm, if it is not already over, or the final later, whenever you have code like this, let's say in this case it's linked list, right? Then I build the next one, and I won't stop at 2 nodes. Because 2 is not an interesting statistic, whether the moment you jump from 2 to 3 nodes, it becomes complex. So there could be questions like giving a question on inserting in the middle of a linked list, okay? Or inserting at the end or insert the beginning, right? The moment you say 2, what does insert in the middle mean? It doesn't make sense. Whereas 3, it makes sense. I mean, generally you don't say middle, you say after the first node, after the second node, and things like that. But in general, I would quickly draw three nodes if you are asked to write some kind of an algorithm related to linked lists in an exam. Because with 3 nodes, all you need to know is it has a pointer, right? Going to the next one and then the next one. So you can easily see whether your algorithm works or not by doing a trial run with some data. Okay, that is what I was doing here. I just built the first node, but I have not continued. But you can continue like that with this code and convince yourself that this code works. Okay. Similarly, we showed other functions there, right? A whole bunch of slides which shows rest of the functions. Then I left off saying that, hey, write a function for counting the number of elements in a linked list. I said, take it home and then you do it. Now, has anyone done this? These two? Write a function for counting the number of nodes and write a function to display the elements of linked lists. I do not know if anyone has done it or not. You can put it in the chat. I did not get a chance to go to the community. Maybe somebody posted there. If so, you can let us know. Okay? Sorry. Then we started off saying that, hey, in the next class, we are going to talk about the polynomial representation using linked lists. Okay? Right? What does a polynomial have? It has 2 fields, right? It has an exponent and a coefficient. So when you are given a big polynomial expression, how do you save it? This is a representation: exponential, coefficient, and link. And I showed you this example, 3x squared plus 5x plus 7, how that is saved. Okay? And then we said we are going to continue the discussion of that. So that is what we will do today. Okay? The intent was to show you quickly some examples of how polynomial expressions are saved in linked lists, show you some illustration of code, and then end the class, and then review any material if you wish to for your midterm, if it is not already over. Okay? So if you are done early, you will go home early. So here is an example. I'll put it in a presentation mode now. Okay. So pictorially, that's how it looks like. This shows a polynomial expression 3x raised to 14, 2x 8 plus 1. Okay, that is the top one, and the bottom one shows b 8x 14 minus 3x 10 plus 10x 6. Okay. Now, the interesting thing is, how do you add the polynomial expressions? How do you do polynomial addition? By the way, I have to go back and refresh my 6th grade, 7th grade math to do this. So you first start off adding if the coefficients are the same, you add, not the coefficient, sorry, what am I saying? The exponent. The exponents are the same, you add them, right? So in this case, the result is what? What is the result of the addition of these 2 expressions? Can somebody put it in chat? You can put it in chat while I'm continuing. I cannot really continue. If I continue, I'm giving away the answer, but that's okay. So, what are we doing here? We are saying we want to do the addition of those 2. And the way the addition is done is, you can see that these exponents are the same. So you add the coefficients, right? So the exponent carries over the very first addition, right? And then you 3 plus 8, 11. So you see C. So that is the first linked list node of adding the first term of these 2 polynomial expressions. Okay? So condition is the a of exponent, meaning polynomial expression a, that exponent is equal to the b of exponent. The exponents have to have the same value. Okay? If I continue, next one. What happened here? You took the next term of b and you took the next term of a. The exponents are not the same. Right? Because one is 8, one is 10. So since they are not the same, one of those two should be the next term of c in the polynomial expression. And as you know from basic arithmetic, the higher exponent comes first. Okay? So that's the reason why the 3 and 10, which was marked in red above, came down. So that was the second expression. You can see the color coding on which expression we are, it is pointing out. Okay? Next, after 10, then you're getting the 8, exponent 8. Okay? Then what do you get? Then you get 6 and then 1. Okay? That is how it works, right? That is a polynomial addition. Now, how do we write code for that? Yes, visually it was pretty easy to explain and we kind of know it mathematically. The trick is to write a code for that, right? So when you have a linked list, it's, as long as you know, as long as you understand the traversals that I gave you on the previous slides of how to go through a linked list and look at stuff, then you should be able to write the code for this too. Okay? Now, when you have this, you can see how powerful linked list is, right? For adding polynomial expressions based on the previous slide. Okay? So we have a linked list and then we dynamically store the user input. Okay? Of all the polynomial expressions. I'm going to show you code for that. And then we add those two polynomials using some rules. Okay? So the code is, at least from a pseudocode viewpoint, we first create an abstract data type using struct. That is what we did, right? The node is linked list node is represented to a struct. Okay? Then you have different functions for creating a polynomial function and adding polynomials, and then also showing a polynomial expression. Okay? And then there is a main function which is always here, driver function, to test your code. Okay? Let me see what we have here. Okay. So the code has to be split into multiple slides because this doesn't fit in here unless I use font type 10. So we are adding two polynomials using linked list. Attribute to the author. How do you say? Swasthata. Okay. So whoever that author is, okay. Include stdirh. These are the libraries. Okay. And then the structure for the polynomial is a linked list. Okay. Now, unlike the other linked lists that you have seen, here you have two data values. So for example, you have seen one data value. But I never said that data value has to be only one. It can have multiple data values. And then finally, there is a pointer to the next node. That's why you see struct linked pointer, right, star next. So this is your polynomial. And it's named myPoly. And if you recall, I told you from the compiler perspective, you need to have these type def things defined initially, a function prototypes, not type def, sorry. That is forward declaration, right? The compiler would know the code, the body of the functions would be coming later in the code, but in its tables called symbolic tables and things like that, it creates room for them in the tables internally, the compiler. That's why you have these prototypes listed here. So you have a prototype for creation of the polynomial, to display polynomial, and then to add polynomials. Okay? So let's start with the main function. Okay? So you have a do statement. Somewhere here, do will have a matching. Let me go here. Sorry, I'll put it back in a big mode here. But you can see there's a do here and there's a while here at the end. Okay, let me go back to this one. It's basically like a loop. You declared my poly is struct. Remember that was a node, right? How many you declared? You declared 3. Why did you declare 3? Think of it as polynomial 1 and polynomial 2. They both get added to form polynomial 3. Okay? So you're saying first job is to create the first expression. So to create the first expression, you call the function myCreate poly address of poly1. So whatever that expression that gets created is saved in poly1. Okay? Then once you create that one, the author is also doing a display of that. That is myShowPoly. So it is going to get some input from the user, create it, save it in poly1, and display poly1. Okay? Same thing for creation of the second expression. Okay? The next 4 lines, right? And then once you do that, then you are going to add the polynomials. When you add the polynomials, you are saying, hey, poly1 and poly2 are going to be added, and then they are going to be saved in poly3. To save them in poly3, you need to pass the address of poly3. That's why you see the ampersand sign there. Since the author wrote good code, they want to test what they have done, so they call the function myShowPoly to see whether they got the right answer or not. Okay? And then, of course, they have add 2 more expressions. So you're in a loop till the user picks 0, right? So once it's 0, that means the do while will stop because the condition would turn into false, and then you come out. Okay. I'm assuming so far so good. Anyone has any questions? Put them in the chat. Okay? Let's look at the create polynomial function. Okay? So what are we doing here? By the way, even for me, I may not know all the lines of code. Sometimes I might forget, right? The idea here is to illustrate. The idea is not to go through line by line. A classroom is not the place to go line by line in terms of code. Okay? You have to do it outside and then ask questions in the community. We'll cover a few, and then you cover the remaining outside of the classroom. So what are we doing here in terms of myCreate polynomial? So you somehow, to create a polynomial, you need to get all the expression, right? You need the coefficient, you need the power. So that's why you can see here, you have a coefficient and power declared. Okay? How do the variables come? Because the problem domain pretty much, it's almost self-evident, as my friend would call it. It's almost self-evident, if you understand the concepts, right? So polynomial has coefficients and power. That's why you need those 2 integers. Okay? He created a temp node because these kinds of things you may not know right away, but as you start tracing when you do the algorithm, then you'll start creating some additional variables and things like that. Okay? So you need to get malloc, we know that. Right? Temp node, this one line. You're saying temp node, we have to do typecasting to myPoly. That's how the compiler would know how much storage to allocate, because myPoly is a struct. It has 2 data values and a pointer, and the data values are integers, I believe. And then, so based on the integer, it knows how much memory it needs to get. Okay? So you are going to do malloc size of myPoly. You create the first node. Once you create the first node, you know the address of that. Since you know the address of that, you are saving it in node. That is head. Remember the head function that I talked to you about, right? Where I traced it at the beginning of the class today. That is this one. Okay? Instead of calling head, he called it node. Okay. Then in the right side, when you come here on the top, you can see you're getting the user data. And how do you want the user to enter the data? You're saying, okay, enter the coefficient first. Okay? So you're going to store it in temp node coefficient. Okay? Then you're saying enter the power. Then you store it in power. So those are the 2 data elements, right? Okay. So like that you continue. Okay. So if you trace this one, you should be able to see how the addition of the polynomial is done. Okay. So how do you show the polynomial? Very easy, right? Again, showing polynomial is nothing but displaying the contents of the linked list, right? That's exactly what it is because we created a linked list. So here, if you look at the polynomial void myShowPoly function, you're getting the starting point of that node. That's what is being passed here. And then you're saying while node not equal to null. Why does it say while node not equal to null? Again, goes back to the concept, right? Remember when I created the very first node earlier, what did I put in the very first node that I created? In the next node arrow next, I put null. Because that null signifies end of the linked list. There are no more nodes to traverse after the linked list. So that is the reason why you have while node not equal to null. Then all you're doing is printf node coefficient, node pop. And then go to the next. Go to the next node. That is node equal to node arrow next. Okay. If node not equal to null, okay, this is an interesting if statement, right? Why do we say if node not equal to null? Can one of the super sharp programmers tell me that? Faculty members are welcome to answer that too. Why did this author have this node not equal to null there? Any guesses? Okay. Last node. Let's say I simply have, let's say x squared plus x. Okay. Or x plus 1. So what is the node? After I read the node, the last node, when I go to node.next, what is happening there? It's pointing to nothing, right? Because no memory has been allocated, right? So it will be null. Okay? If it is not null, that means there is a node there. You are saying polynomial expression, in this case you're talking about plus, right? X squared plus x plus 1 type of a thing. That's the reason why he's checking for node not equal to null, and it says printf x. Then he goes to since it's in the loop, because it's no longer null, then you go to the loop, print out the next set of elements, and so on. You continue like that. Remember the add that I showed you visually, how the addition is done, right? That is this function here. Okay, so I'll let you convince yourself as to how that function works. And then, continuing the same function there, I couldn't fit it all in one slide. You can see how we have to make sure both poly 1 and poly 2 are true. That means there are still terms that need to be traversed, right? You're doing a comparison. Remember, you're looking at a comparison of the powers, right? If poly 1 power is greater than poly 2 power, then you first print out poly 1. Okay? If poly 1 power is less than poly 2 power, then you print out poly 2. That is this else expression here. Okay? Otherwise, else. Final else basically means they both are same. If they both are same, then what do you have to do? You have to add the coefficients, and then you have to add the powers. That's what this else statement is doing here. Okay? Now, again, I want to reiterate, nothing is easy about programming, okay? You'll probably take, considering you are still second year students and you are learning algorithms and you're learning computer science, it will probably take you at least, I would say, 2 days to write this piece of code. Okay? Now, if that is discouraging, don't worry, because if I have to ask the faculty members to write this code, including myself, faculty members, I am not just saying only you. I'm including myself too. Please note that. Okay, we'll probably take 1 week to write it. Students are much faster. Okay, so this is how the code is developed, but the entire code is developed based on the visual that I showed you. So if you know how to draw those visuals, that's why we did a lot of tracing in our class. If you know how to trace, it's easy to write code. So here is some output that the author put some screenshots. I thought let me show them also. So you can see here the expressions that have been entered for polynomial 1 and polynomial 2. Okay, they display the polynomials, and you can see one at the bottom of the screen. You can see 1 times 1x raised to 1, 5x squared. So basically, it's x, right? X plus 5x squared plus 19x cubed. That is one expression. And then similarly, you have the second expression. Okay, the second expression is what? 2x plus 4x squared. Again, I'm reading at the bottom of the screen. 5x cubed plus 16x4 plus 6x5. And then they did the addition. If you go back and look at the driver program, that's what the program is all about, right? And then you get the expression 3x plus 9x squared plus 24x cubed, blah, blah, blah. Okay? So, let me stop there. Questions, comments, before we take a 5-minute break. I know Jntuk was eager to take control earlier. Jntuk or Aditya or SVCW or DMS. Faculty members want to add any additional thoughts this course, I believe. Would you like to increase what we just covered, polynomial expression addition, representing polynomial and linked list? Okay. Okay. I'm seeing Jntuk students clearly. Show of hands, do you understand half of what I said in terms of polynomial addition? How many of you understood that code when I was walking through? At least 50%. Okay, I see some hands being raised. That's a good sign. How many of you understood 100%? Who wants to raise a hand if somebody understood 100%? Oh, wow, some genius is raising a hand. I don't know whether they are stretching their hand or they are really raising the hand. Okay, now is a tough question, right? Don't feel shy. How many of you have understood 0%? Meaning it was completely bouncer, right? Nobody wants to raise a hand because they want to be nice to me. Let me share a secret with you, okay? I'll be very honest with you. Most of the programming classes that I have taken in my entire career, other than I would say 1 or 2. Okay, I cannot say almost every class, right? In the class it was more for whatever the professor is saying. They give some links. I mean, in my days there were no links, right? They say, okay, look up this paper in IEEE or go look up the Donald Knuth. Pure science students used to take the notes like that and go read it and write code. Now, at least now it's to write code. And at least when I was learning, we had one big computer in a AC room which had to be monitored, and we had to even use punch cards to write code. Okay? Now it has become much easier. Unless you write, you struggle, you would not really understand the essence of programming. As simple as that. Okay. After that brief small lecture, let's take a quick 5-minute, let's do a 5-minute break. This is heavy duty stuff, okay? 5 minutes stretch, get up, go get some water, whatever you want to do. If you want to review this one, it is there on the in the community, the slides I posted. You can download them in the meantime, and we'll be back in 5 minutes. Like probably in 3 minutes, back in 3 to 5 minutes, okay? I'm going to get my tea. Okay. What next? By the way, it's good to see students in the classroom. I hope you all had a wonderful Independence Day, and I hope you had chance to look at the nice Hindi movie that got released. What is that movie? Mohenjo-daro and Rustam. Has anyone seen Rustam, JNTV? Show of hands. Okay. I don't know if you guys see Hindi movies there in Kakinada or Vijayanagaram. They release them on time. Great movies. Here we are all very crazy about Hindi and Telugu movies. So we watched them. They are great. I recommend you go watch them. Maybe you'll go watch Ma Babu Bangaram, I guess, Venkatesh movie. Okay. Let's go back to lecture. By the way, I did watch that movie also, the Venkatesh movie, because I'm a big fan of Nayanthara. Okay. Sparse matrix representation using linked list. This was the other last topic of that module 3. The thing that was not clear from the syllabus, and I asked for faculty members to send me some email, hey, am I going too deep or beyond what syllabus is saying, or am I covering everything that syllabus is saying, or am I covering less? Definitely I'm not covering less. I know that for sure. Okay? But for the sake of completion, I thought let me continue with this sparse matrix and show you a little bit of that. Not at the level of detail that we did with respect to polynomial addition in the course, but a little bit of that. Okay. So what is sparse matrix? By the way, we call it matrix in India, and here I'm used to calling it matrix in the US. So if my pronunciation is screwed up a little bit, please bear with me. Okay. Okay, so sparse matrix is a matrix which contains very few non-zero elements. Okay, just a question of knowledge, right? So what does very few non-zero elements mean? Okay, so you can see here in the second bullet, right? You have a matrix of size 100 by 100. It only has 10 non-zero elements. So 100 by 100 matrix is what, 10,000 cells. Out of that, only 10 of them have non-zero elements. It's totally sparse matrix, right? So, if you were to allocate memory for that, space, or I would say, yeah, memory, then how much you have to allocate? 100 times 2. I don't know why the author said 2 here. It depends on the computer architecture, representation of, for an integer, how many bytes of data you store. Okay, it could be 4 bytes, it could be more, right, depending on the byte size. Here they are assuming 2. So that's 20,000 bytes of space to store this integer matrix. Okay. So now to access these 10 non-zero elements, potentially you have to make scanning for 10,000 times. Okay. So that's a lot of memory wastage, a lot of performance hit. Okay. So what computer scientists, actually even math guys, not just computer scientists, or numerical analysis science professors, right? They have figured out we don't need to store the full matrix. We can get by in some cute little ways. Okay? Now, one of the cute little ways that we can get away with having to use that many bytes of space is we can use a linked list to represent a sparse matrix. Okay? So how does it look like? Let me go over here. Some representation here. So it has a 4 by 5 sparse matrix. Okay. So if you look at the bottom right figure here, I'm showing my cursor here, right? 1, 2, 3, 4. That is columns. 1, 2, 3, 4, 5 rows. Okay. So H0, H1, H2, H3, H4, 0 to 4, 5. And this one is 1, 2, 3, 4 by 5 matrix. Okay. So that's a visual representation as to how that is done. And the way it is done, let me see. I'm stumbling here because, give me a second, unless I have written it down. Yeah, there it is. Okay. Let me come back to this slide after I do this one because it's a little bit easier to explain. Similar sparse matrix. Okay. Okay, on the left side you see the sparse matrix. Let me increase the size there. Give me a second. Let me increase the size here. Bear with me for a second. Sometimes we forget when I look at pictures, suddenly we forget something. This is much easier to explain. So you have a sparse matrix here. The number of columns. Okay. Now, then if you look at the rows there, 0, 1, 2, 3, 4, because naming convention is from 0, right? So, and then you say, first of all, the very first row in the table, on the right you see a table. That is where you keep track of all the values in the sparse matrix. We took a 5-row, 6-column. We converted that into a small table. The table basically shows 3 columns saying, hey, in which row, in which column you have a value. Okay? What we are saving is, we took that big matrix on the left, converted it to a smaller table with less number of entries. Okay? Which row, which column has a value. So the very first line is called metadata. What metadata says is, hey, this table has 5 rows, 6 columns, and the total number of values that are there, meaning there is something non-zero value, is 6. Okay? So first row is metadata. If you took a numerical analysis class, you would have learned this too, by the way. Okay? So reading down in the table, I'm saying row 0, column 4. So let's go to row 0, column 4. 0, 1, 2, 3, 4. What is the value there? 9. Okay. Next you go to row 1. Row 1, column 1, because the indexing is starting 1. The value is 8. You see that? So that is how you store the sparse matrix. Okay. So what this other picture was showing was basically a little bit of a linked list representation. Okay, we'll come back to that if necessary. Okay, so the way we do that is to store it in a linked list. Now we have the table, right? We want to store that. So there are 2 main concepts here. One is called, we create a header node, and then you have another node called element node. Okay, so the header node shows some index value. Okay, and then Of course, you have down and right, because either you go down or you go right, because it needs a pointers, right? Once you have the header node, from there you can either go right or you can go down. The big picture, the big pictorial was showing that. And then you have the element node. Element node, of course, has again row, column, value, as we have seen on the previous slide. And then from element node, you can either go down, you can go up, or you go to the right. Okay. Okay. So, very hard to read this slide, I understand that. But pictorial representation, maybe I should go back to the other one now to read it better, right? You can see this one here, the header nodes, whenever you have an element. So let's try to understand this element. Faculty members help me out if I'm screwing it up. Okay, so you have 2000. Okay, so where is that value 2 there? How do I read this? I'm not able to explain correctly. Give me a second. 200. 2 is pointing to 1. Okay. Okay, I got it. Okay. So you have this 2000 is row 0, correct? You're all with me? Remember, indexing is starting from 0. Okay. So indexing is starting from 0, head 0. Okay. You can see that is 0. Okay. The value is 2. The value is 2. I'm not able to explain this. Give me a second. Chakravarti garu meeku an explain cheyagalugtara or any other faculty member? Come on, one of you volunteer. My brain is not working today to explain this. Give me a second. 2002 104 104. Okay, I'll come back to this. I'm sorry, I'm not able to think properly to explain this one. When I created the slide, I was able to. 4003 4003. Maybe the explanation is there in the next slide. Let's see. Hopefully the explanation is there. Okay, this I was able to explain. Yeah, this is a little bit hard to read. Once I put it in the community, it will become easy. But what I'm basically trying to do there is, I'm doing a header node. The concept that I'm using is this. I'm using a header node with an index value and then down and right. And I'm using element node, which shows row, column, and value. So if it is row, column, and value, and then down, up, and right, okay? One more time. Generally, I don't like to give up. Down, up, and right. Okay, 0, 0. Okay, I got it. Okay, now I got it. See, there you go. Now I'm happy. My brain is working again. Okay, 0, 0, 2. So what is this one? Row, first element row, column, and the value. So in 0, 0, row 0 and column 0, you have the value 2, right? That is what this is representing. And is that the header 0? Because that is where the head is. The header is pointing to that very first element. Okay? So if you look at from H0 from the top, you can see from there you're pointing the first row, first column. The value is 2. Okay? Now, if you go to 1, header 1, that is row 1 here. Row 1, it says was first column, row 2, right? Second row. So you can see here 104. Okay, the column is the first value is row, right? 2. 2 means, it's a little bit confusing. We call it 1 because we start with 0, right? So row 1, column 0, the value is 4. Okay. Okay, now I got it. I'm able to explain each and every value. Okay. So one more time with feeling, right? So if you go to H0, the way 0, 0, 0 is read is 0 row, 0 column, value is 2. When you go to the next row, row 1, column 0, the value is 4. So going down like that, if you see in H3, you have what, row 4, or in this case we call it row 3, which is technically 4, and column 0, the value is 8. Okay? So you created a matrix like that, H0, H1, H2, H3, H4, depending on your row matrix count, right? Okay? Then you start filling out the values like that. Values are in red. Okay? So that is how you do that. And then if you go to the thing here, the header node concept here, from that value, where do you go? Do you go down or right? So the two values. That is what this picture is showing. From here, where do you go? From 002, you are going to 104. So you're traversing it like that. Okay? So it's building those arrows like that appropriately. So ultimately, when you do that, does it look like a list to you, like a linked list to you? It has some kind of data values and it has arrows pointing to the next linked list, right? To read the value, right? Because there's a way of reading a matrix. You can read a matrix two ways. That's another important concept, right? You can either traverse a matrix row-wise. We learned that in intermediate, if I'm not mistaken. Okay? When you did the matrix addition or matrix multiplication. So depending on how you traverse the matrix, you can build the arrows accordingly. Again, I'm just showing you a conceptual picture. I don't think they will ask you an exam question to draw a matrix like this. But if they do, let me know, I'll explain it more. Okay? So here is some more explanation. So I was struggling with it, but I could have simply did a hit, return to get to this slide, right? But here you can see H0, H1 to H5 indicate the header nodes, which are used to represent the indexes. Okay? Because we need the 0 to whatever the dimension of the matrix, right? Remaining nodes are used to represent non-zero elements in the matrix, except the very first node, which is used to represent abstract information of the sparse matrix. What does that mean? It's like in this case, if I have to, with your permission, let me go back here. Remember, we had the header node there, this 566. We still need one additional piece of information. So that is what this is referring to, right? Except the very first node, which is used to represent abstract information of the sparse matrix. Okay. Now, in this representation, the representative at least I am showing there is in each row and column, right? The last node right field points to its respective header node. Okay. So that is how. That's the reason that last part is what threw me off. I didn't remember that. So that's the reason why you see the node's right field is going back to the header node. That means it's kind of creating a circular linked list in a sense. Okay. Okay. Questions, comments. I stopped here with sparse matrix to show that basically the idea is to say that, hey, we can show a sparse matrix as a linked list. That's what I did. And the way I have done it is we first take this matrix, convert that into a table like that for easy readability, and then remember the concepts of header node, right? And then the element node. Element meaning every value there, right? And then at the end of the last node, those are the main concepts. I have not shown any code about this one. I'll be happy to post the code in the community. I was not sure actually whether number says yes, put the code, I'll go ahead and do that, okay? You can send me an email. So that basically completes all the 3 units. Okay? So what exactly did we cover in all the 3 units, right? So let's do a little bit of review here. That will come in handy for you. But in order for me to do that, I have to open up a document here. Bear with me for a second. Where do I have it? Notes for the class. Let me open the document here. Let me also open one more thing here. Okay. I'm ready to share some things with you now. Share Word document. Okay, I'm sharing a Word document. I'm hoping you are able to see it. So if you look at the syllabus here, we'll do a little bit of a review for you, okay? So we started off talking about data structures, right? Introduction to data structures and definitions and things like that. Okay, that was the primary thing there in Unit 1. And after we defined that, we said, hey, there are different types of sorting techniques, right? We talked about bubble sort, insertion sort, selection sort. Okay. Again, I typically don't memorize what the sorting algorithms are. There are different types. But depending on what type of exams are given in your internal exam, you may have to memorize some of those things. Here in my class, I give them the algorithm and ask them to analyze it. I don't ask them to write the algorithm, what bubble sort is, what insertion sort is, and so on. Okay. Then in Unit 2, we went into, after laying the groundwork to basic array in Module 1 or Unit 1, when we went to Unit 2, we started getting into abstract data types called stack and queue. Okay. So, and then when we talked about stack, we basically talked about all the different types of stack operations, which are primarily push, pop, and top. Remember? Push, pop, and top. We reviewed push, pop, and top extensively through examples. Okay. And then we said the applications of stacks and queues, we looked at how we can use, for example, reversing a list or factorial calculation. Right? We also covered infix to postfix transformation. Right? Stack comes in very handy for doing those things. Okay? We did similar things for queues as well. Okay? Now, the big difference between queue and a stack is last in, first out, and queue is first in, first out. Okay? In the case of a stack, everything happens on the top of the stack. Whereas in the case of a queue, deleting or getting out of the queue happens from the front, and then adding to the queue happens at the back. So you need two variables to keep track of front and back in a queue. Whereas in the case of a stack, all you need is top of the stack. Okay? So once we did the stack and queues, then we got into, by the way, before I get into Unit 3, in Unit 1, in order for me to explain some concepts in terms of the different sorting techniques, I had to introduce the concept of linked list there also, if you recall. Okay. But we covered a little bit more detail on linked lists in Unit 3. Okay. As you can see from the notes or the data, whatever you call it, data sheet here, there are different applications of linked lists, right? And we looked at a couple of them. Including representing polynomial expressions and sparse matrix. Okay? Sparse matrix, I would say that we didn't really cover it in, I'm not 100% happy with how much I covered. I'll be happy to cover more if you need me to, or I can post some notes there. But we did cover polynomial expressions. We looked at other applications of single linked list, right? We looked at reversing a single linked list. We covered all of those things. And somewhere along the way, I showed you enough pictures of circular linked lists and double linked lists. And when we talked about application of linked lists and so on, we said, hey, when you take the operating systems class, you would learn a lot more about these things. That is where we left off. Okay? Now, we started creating some notes. I think I posted this, right, in the beginning. If you look at it, we start creating notes here in terms of defining what a data structure is, I gave you basic types of data structures. We said we'll cover linked list and stacks before midterm, and after midterm, when we come back, we'll do tree and graph, right? I posted this, if I'm not mistaken. I gave some pictures of how different types of data structures are there, right? We differentiated between the built-in data structures and the user-defined data structures. I gave a definition of algorithm in Unit 1, right? The definitions are there. And then we said whenever we talk about algorithms, we need to talk about the performance of an algorithm. Ultimately, what distinguishes a super-duper programmer versus an average programmer is super-duper programmer knows how to write efficient algorithms. And how do you define efficiency? There are two ways of defining. One is time complexity, and the other one is space complexity. Okay? And then we define what that space complexity means, right? Basically, how much memory your program takes is the space complexity. Okay? And the space can be divided into instruction space, data space, and environment space. And then we went into analysis of time complexity, and then we, for bubble sort and so on, we talked about the big O notation. Remember the big O and data, then the notation that we covered. I looked at your syllabus again later. We are not supposed to cover to that level of detail those complexities, but you got it anyway. Okay. And I asked you to write down some code to get a feel for how to implement these algorithms in the programming language class that you're taking. Okay. What else we covered there? Yeah, I think that's it. And we basically said, hey, what is the worst case, average case, and best case? And that is where I gave some examples to show you there are better ways of doing algorithms. When you do linear search, we talked about order of n, right? If you recall. And if I remember the example of an unsorted array, and I'm looking for an element in the array, the worst case is that it traverse all n elements of the array because it's unsorted. And then we said, hey, if I sort the array and if I use a binary search technique as opposed to linear search, I can keep dividing my search space by half, right? So my order of performance would become log of n, right? We did some examples of that, and you also worked on those examples in the class. Again, all of those things are listed in the notes here. Okay. Wow, these are a lot of notes. Okay. A lot of notes on complexity. Yeah, I'll stop there anyway. I posted this in the community. You may want to go back and review that. What I did not post is I did not include the things that we covered in Module 3. Module 3 is almost like code and visuals, right? So what I recommend is you just review the slide deck of Module Unit 3. Okay, that I've posted over the last few weeks, and I'm going to post this updated slide deck also in the community after the class. So between the notes that I posted there and in Module 3 slide deck, you should be good. So when exactly is your midterm in this case? If you have already finished it, that's good. If you have not finished it, hopefully you can use these things and then review and then go ace the test. Now, some couple of administrative details. Do we have class next week or do you have holidays because of midterms? Can somebody post it in the chat for me, please? Do we have class on Sunday night? That's Monday morning your time. Nobody is there to post the answer for me? Okay, so send me an email. If Chakravarti is still there, I know he is busy today. But send me an email if we have class. Are you done with the midterms, or this is the last week? When are you doing the data structures midterm? In case you have not done it already. And do different colleges do it on different days? Because I have no clue, because I have no control over your midterms and so on. So let me know, either in the chat or you can send me an email. So I'm going to post this one in the community, and then between the notes that I posted there earlier and the slide deck for Unit 3, you should be good. You should be good to go. And students, if you have any questions, just send them to me, and I'll be happy to answer them. Okay? It's best if you email them to me, because I don't check community every day, whereas I check my email every minute. Okay? If anybody wants an extra class, if the midterm is not done, and if you need to take the test, you need one extra class where I can clear all of your doubts, I'll be happy to do that too. Okay. Well, a lot of people joined today. That's nice. Last session, I did not see this many people. Okay, questions, comments, I'm done. I'm done for the day. How come I don't see everyone? Earlier at the beginning, I asked some faculty members to mail me some sample internal exam papers, but I never received any internal exam papers, so that way I cannot really tailor my lecture to the test. Okay, but hopefully you got some knowledge to do the test well. Okay. DMS video మీది కొంచెం కిందకి చేస్తే I can see the students well. I only barely see the top of their heads. Okay, then I did not give any quote, but let me give a quote that a Cisco manager tells often to his team members. Work hard, team. Okay, so I'll put it here too. Okay, JNTV, you're ready? Did you already take the exam, or you're about to take the exam? Well, give me some idea. You guys are so shy. Okay. I will be posting it. I'll be online still for the next few minutes because I'm going to be posting this slide deck. You can watch me do that if you want to. Let me save the deck here. And then I'll see if I can put some notes around this matrix, okay? I'm still not 100% happy with my presentation on the sparse matrix. Maybe I'm biased against it. I'll expand on what I explained in a better way in the notes. How about that? Okay. See, I told you not every day we can explain everything perfectly, you know. We can screw up sometimes. Okay, I'm going to post it in the notes. I don't even know what my file size is. First, I have to check my file size. Let me check my file size. Yeah, this should work. Okay. Unit 3 updated, Unit 3 updated, attach a file, choose a file. Somewhere I put it in Jntuk. See, to teach this class, how much preparation I have to do. I have to review a lot of material, put the best stuff there. We have to work hard to teach classes. Okay, I'm loading the file. Okay, it is posted. Okay, I posted the slide deck, and good luck, everyone. Okay.